two topics, not necessarily closely related, but left, that I wanted to talk about. The first one is one of the books that I use as reference called Bioinstrumentation. In other words, ways to measure things that happen to you biologically that are relevant to workplace design, relevant to ergonomics. And then secondly, something that is really important in ergonomics is anthropometrics. That's the last topic of the semester then. So let's talk about some bioinstrumentation. There's a whole bunch of references here. These are the ones that I used for the material of the lecture. Like I said, this one, this Freybold's book, The Biomechanics of the Upper Limbs, is really a very, very good book. If you are interested in ergonomics and interested in getting into it, I suggest adding that one to your library. It's a pretty good one. EMG, electromyograms. And so we have we already talked about EKGs or ECGs, electrocardiograms, which measures the electrical potential of the heart muscle. And then there's also electroencephalograms, which measure the electrical potential of the brain. And then there is electromyograms. So it's myo, it's muscle, right? Measures the electrical potential of your muscles. There are three, and by the way, there's some problem associated with this, because if I, and this is most common, if I paste an electrode to the surface of a muscle, well, how do I know that I'm picking up only that muscle? There's a lot of different electrical impulses going on in there. So, and when you get a bunch of different muscles, pick up the electrical signal of them, that's called crosstalk between the electrical signals from the muscles. So, in order to overcome crosstalk, there's several different approaches. The surface electrodes are the ones that we use occupationally. And those are the ones that are the least accurate, have the most crosstalk, but you don't need a medical degree to use them. So that's the ones we stick with. The other two are usually used for clinical applications. Those are wire and needle electrodes, just as the name implies. You can pinpoint a muscle very well, but you don't get very natural motion out of it because you have something actually embedded in the muscle during activity. And without local anesthetic, you really can't get very good motion, especially if it's a wire. It's not quite so bad because it can move around, but they do have a tendency to get bunched, yes?
You said without local anesthetic you won't get very good motion. Will the anesthetic...
Because of the pain.
Correct, but will the anesthetic interfere with the results?
Probably.
Okay.
Probably. That's why I said that for the applications we get, you eliminate crosstalk, but you wouldn't be able to do most of the activities
Correct.
that you want to do occupationally anyway, so it doesn't really matter. And it's just what the name implies. You have a wire that you embed in the muscle, or you take a needle and stick it in the muscle. Both of them not very good options for lifting and doing that sort of thing. So we deal with crosstalk and we use surface electrodes. And typically you use a positive and a negative and a ground. So there's usually three attachments for any measurement, and the ground typically you use a bone of some kind. So it would be like an epicondyle, or the sternum is usually a pretty good ground. Knee, anywhere that there's a bone very close to the surface is usually a good ground for a surface electrode. Don't get too involved with this. This is just, I just wanted to give you an example of the type of things that you can pick up. There are three different signals in there. One is called the nerve action potential, or the NAP train. One's called the muscle action potential, or the MAP train. And the other one is called the motor unit potential. Okay? And those are fairly obvious. The nerve action potential picks up the activity of the nerves in the tissue. The muscle action potential picks up more than one muscle, okay, more than one motor unit, and then there's the motor unit itself. So with all of that going on in there, you get a fairly messy signal, usually with electromyograms. And that's all I wanted to get across with this. I'm not going to, like I said, this is just to give you information, because it's picking up from the skin, from the surface, what's going on in each one of of your motor units. And then, like I said, there's a potential it's associated with nerves, with the entire muscle and other muscles, and then the motor unit itself. All of that goes on simultaneously to make it very messy. Because of that, has anybody ever seen a raw electromyograph readout? Have I ever seen that? What it looks like is if you have time going in that direction, and here you have millivolts or millielectron volts, and here's positive, here's negative. It's a jagged series like this, and sometimes it'll have higher peaks, and it just continues like that. That's what the signal looks like, because there's all these superimposed polarizations and depolarizations, and this is the raw signal. Okay. One of the things you can do to process it, one of the things that happens when you process it, is to rectify it. And when you rectify it, essentially what you do is that you take everything that's negative and make it positive. Well, let's assume that I'm going to try to superimpose that, because it's just scribble anyway. But when you take everything that's negative and make it positive, then it's rectified. The next step, and this is the most interpretable step, is integration of the rectified signal. And with integration, you do it over time, but you'll smooth it out into something that looks like a function. Okay? That the rectified integrated signal then has a magnitude associated with it, and these are amplitudes here. Or it can also be, it depends on whether you're talking about frequency or time domain type of thing, but this is a time domain where you have amplitude. There are many things that influence an EMG signal. Okay? How tired you are, how sincere you are in exerting force. Okay? There's not a really good relationship between force and EMG amplitude. The amount of voluntary contraction that you're exerting. All of these things influence the EMG signal. There's an attempt to make a relationship, and again, I'm not going to ask you this, okay, as far as meaningless calculations, but what this is meant to indicate is that there's an attempt to normalize, where you take the signal at any given time minus the minimum signal, and then the entire range of your EMG. That's your normalized EMG signal. Okay? And then you can take that normalized EMG signal, and this is a typical way to calculate. It's not a linear force relationship, where you have the gain normalized EMG signal, the length of the muscle during contraction, the velocity of the muscle during contraction, and the force exerted by that muscle. What's the passive tension of that muscle? Okay, if I just have an untensed or an unflexed muscle, and it has a natural elasticity, a natural tension that it exerts, and that goes into the relationship. So you can see that there's not any easy linear relationship between EMG and force. That's all I'm trying to get across here. It's influenced by a lot of different things. Nor is it even linear. Okay, time versus, and this is biceps brachii, average EMG amplitude. It looks like it doesn't look like there's a simple linear relationship. This is a sort of a quadratic relationship that we have to try to model in order to infer force from EMG. This is a really interesting result, and this is used in workman's compensation sometimes for a variety of different things. Like I said, how sincere you are in exerting force will influence the EMG signal. So, if we have someone who says that they can only exert so much force, if this is the force, maximum voluntary contraction, and this is your rectified EMG amplitude, if there is a strict linear relationship, that means that they're modulating their force exertion. Right? There's not, in other words, they're modulating it so that they're linearly increasing force as they're increasing the activity of the muscle. Right? That's not sincere. If someone is sincerely exerting as much force as is possible, there will be a kink. As they get past 50% of their maximum voluntary contraction, there will be a sharp uptick in the EMG amplitude. So this is more of a, it's either a piecewise regression. Have you guys talked about piecewise regression in QM at all?
Say that again?
Piecewise regression.
Piecewise? No.
Okay. Piecewise regression is where you take a section of your data, fit one line, take the next section of your data, fit another line, and so on. However many groups of data you feel can be separated. So you can either do a nonlinear quadratic fit, or else you can do piecewise. In other words, up to 50% maximum voluntary contraction is one.
Multiple regression?
Pardon me?
Do you call it multiple regression as well?
No,
Multiple.
multiple regression is
Or
something
linear.
else.
Linear?
Yeah, this is linear.
Yeah.
Yeah, you could do it, and like I said, you could possibly do a nonlinear modeling, but piecewise is probably the best way to do this. But anyway, the point is that you do piecewise from 0 to 50%, another regression model from 50 to 100%, and if you have that kink there, so that you have to do the piecewise regression, that's a true exertion of force. So they may use this sometimes to identify people who are not as injured as they say they are, or something like that. This is kind of a forensic application of EMG signals.
I love the title of the one on the left.
Oh, faker. Yeah, I know. I considered whiting that out and calling it something else, but no. It was more positive than it was worth. It has some entertainment value. This is from Freyvolds. And actually, he was my master's thesis advisor, and that's one of the reasons I left it in. If you know him, you would know that he would be, he's very blunt. Let's put it that way. So I thought I'd just leave it in. It's awesome. It was interesting to have him comment on my thesis. That's all I'll say. Another relationship with EMG and fatigue is with fatigue. This is a power calculation, but it doesn't really matter. Whereas this is in the frequency domain, where we have the center frequencies, because you can decompose this into frequencies, right? According to the number of the frequency of the signal. So if you decompose it into its frequencies, up to 100 hertz, when you're fatigued, you have more lower frequency, and it makes sense. I mean, you don't have as much muscular activity as you fatigue, so you have a shift in your center frequency. Okay, a shift from about 45 hertz down to about 10. So there's a shift in frequency as you fatigue. It's another interesting relationship with EMG is it's influenced by fatigue. And I just wanted to mention, we do a lot of, for this class, we talk a lot about motion analysis. We capture motion and we find the joint center location in three dimensions, and that's the way we do most of our analyses, and that's predominantly a way that you do it in the lab at least. When you get out into industry, most of our lab motion capture devices aren't very usable. They're not friendly to taking out in field applications. And if you want to get a relative measure of angle, what we use is goniometers. Okay? A goniometer, all that means is it's a measurement of angles. Okay? Goniometry is just a measurement of angles. We happen to be interested in the measure of joint angles. There are two types of goniometers that are in common use, and because most of the things that we experience are problems with the upper extremities and problems with the back, the two most common ones are wrist and elbow goniometers. They'll measure the angle in 3 dimensions. The wrist usually flexion extension, ulnar radial deviation, and pronation supination. At Ohio State, they developed a goniometer for the lower back, and it's really just an exoskeleton that measures the amount of twist and the amount of bending and it has this sort of pseudo vertebra in the lower back region, and it's used pretty extensively to evaluate the motion required for different jobs. These, however, both of them have problems with crosstalk, because very rarely do you just do a flexion without an ulnar deviation, without a twist. And when you do that, you get crosstalk between these as well. So now there is a goniometer that is, instead of 3 different sensors, there's one sensor that will sense all 3 of those dimensions simultaneously, and that's what the lower back, the lumbar motion measurement device does as well. So goniometry is something that's more field usable, and you can get information about motion, at least relative joint angles, during the performance of an activity. The next one is nerve conduction velocity. I'm only talking about this because I probably should move this to the, actually that's a pretty good idea. I think I will do that for next year. It just occurred to me that this is probably best talked about in conjunction with musculoskeletal disorders, because how do we measure whether or not you have any neuropathy? Well, this is the way they do it clinically. This is not a field usable technique. It's not something we use in occupational safety. However, it is something that's used very frequently in occupational and other kinds of medicine, is nerve conduction velocity tests. And they use surface or needle electrodes. Needle electrodes obviously are quite painful, but what they're trying to do is measure the speed with which a specific nerve, like the median nerve for instance, the speed with which it is capable of transmitting a nerve impulse. There are standards. I mean, there's quite a bit of variability, but there is a range that you would expect from a healthy nerve. And what this does is it gives you the speed of nerve conduction, because what it will do is artificially stimulate the nerve. And then one other of the sensors, there's cathodes and anodes. It doesn't really matter which is which, but what happens is that it will send an impulse, and then it will be received by the other one. You know the distance between those two, so obviously you can figure what the nerve conduction velocity is, the speed of it. And I gave you a lot more information here than you really need. I got beside myself, as I usually do. But what's important from this is the idea of sending and receiving artificially a nerve impulse along target nerves in order to determine whether or not that nerve has been damaged or not, because damaged nerves have slower nerve impulses than a healthy nerve. Again, there are people who analyze these, medical personnel who analyze these, to look at the form of the wave, just the way you look at the form of an EKG or an ECG, electrocardiogram wave, where we can tell different things because different parts of the wave mean different things. And these are the parts of a nerve conduction velocity wave. I'm not going to ask you about the details of that. I'm just showing it to you to show you that it's not a simple measure of velocity, but it's a measure of onset. It's a measure of when it reaches peak. It's a measure of amplitude, and then it's a measure of how far positive, how far negative. In other words, how much the polarization and depolarization aspect of the nerve impulse is affected. And just to give you an example, there are published values for nerve conduction velocity. So, and those values are according to the region of the nerve conduction wave. Onset latency, peak, the amplitude, and conduction velocity all have standards with which, to which you can compare your patient's nerve conduction velocity. And here are some other ones. This is for ulnar and radial sensory. This is median nerve sensory, because you have to measure sensory and motor nerves separately because one's afferent, one's efferent, right? Everybody remembers that from the first part of the semester. You have to dredge up those old neurons there, right? But that's what that's what this refers to. These are sensory nerve values, and the motor nerves have similar values. But this is just an example. Skin temperature, body mass index all influence nerve conduction velocity. So if you have a patient that has a very high body mass index, you have to recognize that that's going to increase latency. Okay, you have to take that into account. If somebody is very hot, that's going to influence the latency. That's going to influence the amplitude of the nerve. So there's a lot of aspects of the patient that are going to influence nerve conduction velocity. Okay. Questions on any of those were just to familiarize you with some really common types of instrumentation. EMG is used a lot in the lab. It is not something that is typically used in, it's not something that's typically used in the industry. It's not easily used on the floor because you have to have all these electrodes attached to your subject, and it's not particularly easy to use in industry, but it does have applications. Okay, last topic, anthropometrics. And last but not least, because it's really important in ergonomics. Because if we don't know the size of the people that we're designing for, we're going to have a lot of trouble designing for them appropriately. Best example of bad anthropometrics is in the late 50s, early 60s, when they tried to import Japanese cars to the United States. Okay, at the time, now it's not true anymore, but at the time, Japanese were substantially smaller than the US population. They didn't think about that when they were making cars. They made them for themselves. Tried to import them to the United States, nobody could fit into them. They were very, very poor marketability. That's why in the 60s and 70s you didn't have a lot of, well, maybe by the 70s, but in the 60s, Toyota and Honda didn't exist. Now it's just the opposite. There are probably more of those than there are of the Detroit-made cars. But that was their initial failure, because they didn't consider the difference in size between the different populations when they designed their cars. Because they didn't think about this. Anthropometry, it varies by ethnic group, gender, age, obviously, nationality. Because even if you are ethnically similar, some countries have better nutrition than others, and they will have different anthropometrics because of that. So you have to consider a lot of different variables in body size. And anthropometry is any measurement of the human body. It's linear dimensions, it's volume, it's circumference, and it can be dynamic as well as static. We'll talk about dynamic movement envelopes. So if I'm standing or sitting and I have to use my left hand, what's my reach? Okay? It's going to, if I have to reach across to this side, it's going to be a lot less than if I can reach directly out to the left. Likewise with the right hand. Right? Those are dynamic envelopes of motion that are considered part of anthropometrics. There's a bunch of different tables here that I want to go through relatively quickly, not because they're important in themselves, but they show different ways to measure and think about anthropometrics. This is age versus the percent of stature for different parts of your body. SH is sitting height. Okay. All of these have the same axes. Birth to 16 is this first part of the axis. 20 years of age to 80. Why they skip? I probably skipped that area in there because of the variability of the growth spurt and that sort of thing. But birth to 16, 20 to 80. Let's just take a look at sitting height as a percentage of stature. Okay, when you're born, you're mostly torso, right? And sure enough, it's 70% of your sitting height at birth. It drops precipitously as you become more gangly as a teenager. Okay? That's when you're all arms and legs, when it's just a little over 50%. And then your torso grows a little bit relative to the rest of your body as you age after that. Okay? And these different circles, this is for males is black circle, white circle is females. Okay? So there's a slight difference based on gender, and that's not surprising. Buttock knee length, that's what this is. KH, I can't remember all of these, is knee height. You get the idea. I don't have to go through these ad nauseum. But this is quite interesting. This is a very dynamic relationship between the proportion of different parts of your body and based on gender and based on age. This is grip strength based on gender, based on age. Ranges from 10 to 18 and then 20 to 60. You can see that for males there's a precipitous increase and then there's a decrease later in life. For females it's less precipitous, the increase, but women also experience somewhat of a decrease towards the end of life. Okay. So again, a dynamic, and this is a strength-based relationship. Here we have age, nationality. Well, that's why I said nationality, there's not necessarily an ethnic differentiation. Here we're looking at British and US, males and females. No true ethnic differentiation for the most part. However, there is a nationality differentiation. And if you look at US is square and Britain is circle. Here we have stature is greater for US, and body weight particularly greater. At least these are a little bit older. It's probably the Brits are probably catching up to us by now with weight. But in both of these cases, you can see that there is, even though there's not an ethnic differentiation, there is a national differentiation based on country of origin. This one I thought was really interesting, because here we have sitting height and total stature based on ethnicity. And let's see what this is males, so we're not looking at gender here. But we have European, Indo-Mediterranean is the white circles, Far Eastern is the square white, and African is the black square. So based on your ethnic group, you have a larger sitting height relative to stature. So up here you have the Europeans. Over here you have Asians, Far Eastern, and down here you have Indo-Mediterranean, whatever that is, and then African down here as well. So this is an interesting, I think, an interesting relationship between ethnicity and stature. Okay, and this is only for males. And this is the percent relative sitting height. So this is the 50% of sitting height, 55% relative sitting height. There's a pretty tight range between 50 and 55, but it does vary somewhat. Growth rate. This is age and stature. Okay. The dotted line is female. The solid line is male. Here we have velocity. In other words, the change in millimeters per year. And here you have the famous grow a lot, and all of a sudden there's a growth spurt, and that's the female growth spurt earlier than the male growth spurt. Okay? And then by the time you're 18, you're pretty much done growing. It varies a little bit, but 18 to 20, you usually aren't growing in stature very much anymore. Okay, so that's just a small example of all the things that you can get with anthropometrics, all the things you can do with it, but there's a lot more than that. If we want to use a mock-up and test whether or not we can fit into it, or a population fits into it, something that we use is called fitting trials. And it's just what the name implies. You get people to sit down and you adjust it until it's the way that they're comfortable. And you can get a range that way by using a range of sizes and genders and ethnic groups and so on in your population. And then you get upper and lower limits. That's one way to do it. I already talked about that we can get static and dynamic dimensions. Dynamic dimensions being while you're moving your arm, while you're performing some task. You get a dynamic dimension that will be required in order to perform that motion, your range. These are some typical linear heights, but you can also have specialized. This is standing seated, okay? But you can also have specialized, prone and supine. So for instance, if you're lying on your back working on an engine, okay, that you would have to get different dimensions because we tend to spread out a little bit when we lie down. Right? We gain a couple of millimeters in height, like I already said, because of the compression of the intervertebral disc in the course of the day. So if you have specialized postures like prone supine or something else, you probably should measure your population in those postures because there may be some variability that might be substantial enough to make a difference in your design. Might be. This is an example of a reach envelope. Seat reference vertical is what what that means. In other words, if you're sitting, this is your seat reference vertical from the superior position. This is the seat reference vertical from lateral, and then you would measure according to linear height, what your reach is. You could measure it either laterally. This happens to be an idea of measuring it from the superior location. And notice that there is a 5th percentile, 50th, 90th, minimum, and it doesn't look like we have a maximum one here, but there you have a minimum reach. This is some examples of restrained and unrestrained. I don't want to dwell on these, but like I said, I want to give you the idea of the variety that you can measure. Now this is males, right from seat reference vertical, and you get a range from, and then restrained and unrestrained is whether or not you're wearing a seatbelt that keeps your shoulders pinned, and then male and female. These are the types of charts that you would need if you were designing things like cockpits and designing things like control panels. That's what you'd use this for, this type of data. Typically, yes, I know, I couldn't resist.
That's all.
But typically, what do we get? When you go to an anthropometric table, and I should have brought one along, but the CDC, for instance, publishes anthropometrics of the US population in incredible detail, very frequently. Probably, I suspect that they publish a new one every 10 years at least, probably more frequently, but I'm not quite sure. And how will they usually report the anthropometric data? Well, they report it usually by the mean and standard deviation. Okay? So, if I have the mean and the standard deviation, and let's say that I have a length that isn't in my anthropometric table, but I have all the components of the segments that are in my anthropometric table. Well, that's when I use this typical confidence interval relationship, right? You have mean, you have your tabulated ratio, and then you have your standard deviation, which here we're assuming that's usually standard error there, right? Okay. But for this, they assume that your n is 1, so your standard error reduces to the standard deviation, right? Everybody remember that? Standard error is the standard deviation of the square root of n. And if you assume that n equals 1, that reduces to just the standard deviation. So, usually what we're interested in anthropometrics, you can't accommodate everybody. That's just an accepted fact. It's impossible to accommodate everyone. But what we usually strive to do is to accommodate the 5th through the 95th percentile. That means, what are we interested in? 90% confidence interval, right? And 5th through 95th percentile. But you have to recognize that if it's for US males, then it only applies to US males, and if it's for upper arm length, then it only applies to upper arm length. And you can't generalize it. And you can't add all the 50th percentiles together and get a height or something like that and use that, because no one is 50th percentile for every part, even though you might be 50th percentile height. Chances are lower leg, upper leg, arm, and so on is not going to be the same. It's not going to be 50th percentile. So, what you would do is, if we have, and this I got from a table, it's just a random selection, but we have British males 18 to 45 years of age, 50th percentile is 1745, or about 1.7 meters. Standard deviation is 69 millimeters. And if we want to get 5th through 95th percentile, that's the way you approach it. Everybody remembers enough of their stat to do that. That's pretty straightforward. Okay. Another thing is, let's assume that for some reason, this probably wouldn't be the case, but let's assume that I have a table that gives me upper arm length and total arm length, but it doesn't give me lower arm length. Okay? So it has a component and the entire segment, but it doesn't have one of the other components of the segment. Well, I can estimate, as long as I know the correlation, and this is from Crony, an idea of correlations between different segments, and I can use these relationships. And if it anatomically adds, that means that my lower arm, my upper arm anatomically add to give me the length of my whole arm, right? Make sense? If it anatomically subtracts, that means that my whole arm, and I know my lower arm, then I can subtract that off and get my upper arm from that. That's an anatomical subtraction. Okay? For the means, it's straightforward. You just add them together or you subtract them. However, for variance, it's not so straightforward. You have to use to get the variance of the two segments, or the subsegment, you have to use the variance of each one of your segments, and then you have to either add or subtract 2 times the correlation between the two segments. And you can estimate that, and this is a very, it's a gross level table, but this says if it's greater than 0.7, it's black. If it's 0.5 to 0.7, it's gray. And if it's less than 0.5, it's white, or if it's irrelevant, it's white. So, if we, let's just say waist girth, let's see if I want to find a correlation between waist girth and weight. I look at, that's 14, that's 2 and 14. That means that there's a greater than a 70% correlation, or 0.7 correlation between the two. Here, between weight and 11, which is interacromion width. Okay? In other words, the width of your shoulders. Interacromion width and weight is about between 0.5 and 0.7. There's some relationship, but it's not a great relationship. And between, if it's on the diagonal, it's itself, so it doesn't count. And between something like, a height, it's not good, hip breadth, and weight, apparently there's not a good relationship. It's less than 50%, or less than 0.5, hip breadth and weight. So that's the way you read this table. If I were to ask you this, I wouldn't ask you to read this table, but this is here for one source of data, should you be interested. Okay, so let's look at an example. Lower arm and upper arm, anatomically additive, right? Because together they form the whole arm. And for the mean, like I said, that's trivial. You just add whatever your mean for the lower arm and the mean for the upper arm, and you get the mean for the entire whole arm. However, for standard deviation, it's not. So let's say that I have a correlation of 0.7, and the standard deviation of lower arm, standard deviation of upper arm, put it into this equation. So remember, this is standard deviation. The equation calls for the variance. So it's 69 squared, 72 squared. 2 is a constant. R is 0.7. The standard deviation is 0.69. Standard deviation of the upper arm is 72. And so that means that the variance is this. Remember that you're getting the variance. You'll get a huge number. But however, if I want to know what the standard deviation of the entire arm is, it's 130, assuming a relationship of a correlation between the two of 0.7. Now let's say that I want to look at anatomically subtractive. Okay, the entire leg and the thigh, and what I'm trying to find out is the lower leg. Okay. Lower leg is anatomically subtractive, so we have the standard deviation of the entire leg, standard deviation of the thigh, minus 2 times, assuming a correlation of 0.5, and then 4156. So the standard deviation of the lower leg then would be 50.2. It's a way to estimate if we don't have all the data that you need. That's all that means.
Question.
Yes?
What do you mean by additive and subtract? Why are they like this?
Lower arm and upper arm together form the entire arm.
Okay.
The entire leg, the components of it are the lower leg and the thigh. I don't have the lower leg, so that means I have to subtract the thigh from the entire leg to get the lower leg.
Oh, okay.
Okay. Does everybody understand anatomically additive and subtractive? See, I have a few more pages to go. Why don't you take about 10 minutes? I'm just getting a little jittery, and then I'll finish up.